Starting again with the acceleration being the derivative of the velocity vector, and remembering that the unit tangent vector t is the velocity vector divided by the speed, the acceleration is the derivative of the speed multiplied by the unit tangent vector. Using the product rule, this is the derivative of the speed by itself multiplied by the tangent vector plus the speed multiplied by the derivative of the unit tangent vector. The unit normal vector is the derivative of capital T divided by the magnitude of that derivative, so it then follows that this must be true. We introduced abbreviations a sub t and a sub n for, firstly, the derivative of the speed, and secondly, the speed multiplied by the magnitude of the derivative of capital T with respect to little t. In our previous work, we have figured out formulas that will allow us to easily calculate these two quantities in terms of the velocity vector and the acceleration vector. I want to look at this from a slightly different perspective, though. We have previously figured out that the derivative of arc length traveled per time is the speed, so the derivative of the speed is the derivative of ds dt. It is the second derivative of distance traveled along the path with respect to time. If the tangent vector never changed, this term wouldn't be here, and then literally a sub t is the second derivative of the amount of distance that you've traveled with respect to time, which is what we usually think of as acceleration. To finish my picture, I want to investigate the meaning of this piece. Inside the magnitude quantity is the derivative of the tangent vector with respect to time, but I'm going to write that in a different way. The chain rule tells me that the derivative of the tangent vector with respect to t is the derivative of the tangent vector with respect to s multiplied by ds dt. The magnitude of a number times a vector is the absolute value of the number multiplied by the length of the vector. On the other hand, I know that ds dt is the magnitude of the v vector, and so is not 0. I'll drop the absolute value signs on it, and for now, I'll just write it as speed times magnitude of dt ds multiplied by the n vector. But if I compare this against my original way of splitting up the acceleration vector, it must be true that the acceleration in the tangential direction is the second derivative of arc length with respect to t, which we already knew, but also the acceleration in the normal direction must equal the square of the speed multiplied by the magnitude of dt ds. This is a very interesting formula because I know how to calculate the speed squared. That's easy. I know how to calculate a sub n. We've figured out several formulas for that. The only thing in this equation that I don't know is the magnitude of dt ds, and that's what we're calling the curvature. So this formula is going to let me figure out what the curvature is in a very easy way. The speed squared times the curvature, being a sub n, must be the magnitude of a cross v divided by the magnitude of v, because we have previously used vector trickery to figure out that that tells me what a sub n is. So despite what a person might think, I don't need to know the arc length parameter. I don't need to solve for t in terms of s. I don't need to actually calculate the second derivative of position with respect to arc length and then take its magnitude, but rather I have to cross product the acceleration and velocity and calculate how long it is, figure out what the speed is, divide by the cube of the speed, and I get this number without ever actually calculating s. So this really is, it's like a magic trick. We need to do some examples to see if things are the way they should be. Let's return to looking at a circle of radius b centered at the origin. I can represent this as a vector-valued function in three-dimensional space by letting the x component be b cosine t, y be b sine of t, and z will be 0. I want to calculate the curvature of this using our new idea, so I need to know the acceleration and velocity vectors, I'll need to know the cross product of them, and I'll need to know the speed. Based on what we did in the Calculus 1 discussion, I'm supposed to end up with the reciprocal of the radius. The curvature should be 1 divided by b if this idea is the same as the one we talked about from the Calculus 1 point of view. We could just grind out the calculation, or we could be clever. Both the velocity vector and the acceleration vector are in the xy plane. The cross product has to be at right angles to that. The cross product has a z component, but not an x or y component. So there's no need to split this up into the usual I, j, k, because I already know only the k part is going to contribute anything. If you don't believe that, go ahead and grind it out the usual way, and you'll find out that this is true. Being careful about the plus and minus signs, a cross v works out to be the negative of the radius squared multiplied by the k vector. I need to know the magnitude of that. In this case, the magnitude of a cross v works out to be the square of the radius of the circle. In the denominator, for the curvature, I'm going to need to know the speed cubed, so I have to calculate the magnitude of v, cube that, and then write down b squared divided by that magnitude cubed. This is direct, though. Take the non-zero components of the velocity vector, square them, add them up. The z component would add 0 squared, so I didn't bother writing that. B is positive since it's the radius of a circle, so the magnitude of v, the speed, is just equal to b in this case. Putting this into our formula for the curvature, the magnitude of a cross v divided by the cube of the speed is b squared divided by b cubed. The curvature of a circle, according to these new ideas, is 1 divided by its radius, which is the same result that we got from a much messier calculation using the ideas from Calculus 1. This supports the idea that this thing, magnitude of dt ds, is the same kind of thing as you called curvature in Calculus 1. In the next example, we'll see that that is absolutely true. In a previous discussion, we showed that back in the Calculus 1 context of looking at a graph of y equal f of x, a lengthy calculation involving the chain rule showed that the rate of change of theta with respect to arc length, which we decided to call the curvature, is the second derivative of y divided by the 3/2 power of 1 plus the square of the first derivative. More recently, we call the curvature the magnitude of the derivative of the unit tangent vector with respect to arc length, and an obvious question is the new idea more or less the same as the old idea? And the answer, as we're about to see, is yes. To use all of my ideas, I have to express my curve as a vector-valued function. Since x is the number that tells me y, it seems natural to use x as the parameter. I'll write my vector-valued function as r of t equals t times I plus f of t times j, and since all of these points are going to be in the xy plane, I'll make the z coordinates on the path all equal to 0. After I calculate the curvature, I'll remember that x and t are the same thing, and that y, being f of t, is also f of x. I'll write the previous discussion result up in the corner so that we can refer back to it. It's worth mentioning that the second derivative of y might be positive or it might be negative. People will then sometimes speak of positive curvature or negative curvature. Being lazy again, both the velocity and acceleration lie in the xy plane, so only the z component is going to amount to anything. Since I don't know if f double prime is positive or negative, I also don't know if negative f double prime is positive or negative. So absolute value of f double prime at t is going to be the top of my fraction. I need to divide by the speed also. I also need to divide by the cube of the speed if I want to get the curvature. At this point, I remember that t and x are the same, and that f is the y value. So expressing this back in terms of the original language, the curvature comes up equal to this expression. If I compare this to what I got by doing the derivative of theta with respect to s, I see they are the same except for the absolute value.
I was making a little joke, sir.
Extremely little, Ensign.
Our curvature in the Calc 3 sense of the word can't be negative because it's the magnitude of a vector. Other than that, these two things are the same, so I was making a little joke when I said they were absolutely the same. Another common variation on a theme is when you have a curve described by parametric equations, meaning that x is given as a function of t and y is also given as such a function. In this kind of application, people often use a single dot to indicate differentiation with respect to t and two dots to indicate the second derivative. In what follows, for brevity, I'm going to omit the of t part, so it's understood that x and y are given as functions of t here. By this symbol, I mean find the derivative of x with respect to t and then square that. I don't mean take the derivative of x squared. This is a very big weakness of this way of writing things, so we need to make sure that we keep these things straight. The two dots indicates a second derivative. As before, having found the speed, found the velocity vector, found the acceleration vector, I need to form the cross product of a and v and take the magnitude of this. This will allow me to just write down a formula for the curvature. As in the previous situation, the curve lies completely within the xy plane, therefore so does the velocity and so does the acceleration. The cross product has interesting components only in the vertical direction, only in the direction parallel to the z-axis. Doing the determinant in the usual way, A cross V is the quantity x double dot y dot minus x dot y double dot times the k vector. Since the k vector has length 1, the magnitude of A cross V is just the absolute value of this quantity. In our formula for the curvature, this absolute value quantity will form the top of the fraction. The bottom of the fraction will be the cube of the speed. It'll be x dot squared plus y dot squared raised to the 3/2 power. So, as before, if I have the situation where x is a function of t and y is a function of t, I can just write down a formula for the curvature in terms of derivatives of x and y with respect to t, and then make this a straightforward calculation. This is about all that I'm going to say about curvature, at least at this point, except to mention curvature of surfaces and other things is a very interesting topic, and at some point you may encounter that topic. In the meantime, I hope everybody's having a good day, and I'll talk to you again soon.